The last topic I'd like to cover on discrete time LTI systems is what happens when you put complex exponentials as an input to a discrete time LTI system. And we'll see what you get back out is the same complex exponential, but just scaled and phase shifted. So learning objectives are to use what we call the eigenfunction property to compute the output of LTI systems, and then to show that LTI systems essentially cannot add new frequencies to the input function because all it does is rescale the existing frequencies in the input function or input signal. So in this sense, we can think of complex exponentials as invariants and then the eigenvectors of the linear system. So why don't we take a look at our complex exponential signals in discrete time? We just have a e to the j omega naught n. Right, we want to know what happens when I put e to the j omega naught n into h of n. That is, what is y of n? What is my y of n going to be equal to? Right? And so that's the central question we're going to address now. So starting from scratch, what we can do is just write out the convolution. So here we have, this is x of n minus k. It's e to the j omega naught n minus k. And then we have h of k. And then what you can see is that this e to the j omega naught n can get pulled out. It doesn't depend on k, so we can get pulled out of the sum, and then what we're left with is this term k equals minus infinity to infinity, h of k e to the minus j omega k. And the important point here is that there's no x of n in here, right? So that means this is just a function of h of n. So let's define that function. So let's define this function h of e to the j omega, I'll call it. And it's just this equal to this sum over here, right? And so what we're looking at over here, this thing is then equal to h of e to the j omega naught. So the point is that y of n now is just the same thing as x of n. This thing is the same as x of n. So y of n is equal to x of n times h of e to the j omega naught. And what we'll see is actually that this formula here that we've been looking at, this is actually called the discrete Fourier transform of h of n. So in linear algebra, there's this concept of an eigenvector. I know that linear algebra is not a prereq for this course, but so I'll just give a basic description of an eigenvector. If I have a square matrix and I multiply this matrix B, if I multiply it by a vector V and I get back the same V, this is the same V, and this is a constant, then we call V an eigenvector, because basically B, if you like, kind of leaves the direction of V alone. So V is a vector, it has a direction and a magnitude. B will change the magnitude, but it won't change the direction. So in some sense, it's an invariant direction for the matrix B. And in the same way, when you talk about our vector space of functions, remember we were saying that LTI systems kind of act like matrices. So in that sort of analogy, this applying a system to e to the j omega n is going to produce e to the j omega n, the same input back, but now with this scaling. So this kind of looks like an eigenvalue. It's called an eigenvalue. And this is an eigenvector. And since we think of signals as functions, we call them eigenfunctions. And so the statement we'd like to say is that complex exponentials are eigenfunctions of LTI systems. That's what this means, basically, that you stick in the complex exponential, you get the same complex exponential at the same frequency back, but just with a constant multiplication by h of e to the j omega. So in general, this value here, this h of e to the j omega, is a complex number. So we'll see an example in a little bit. But what that means is we can write x of n in magnitude phase form. So let's look at a new x of n. Let's call this x of n a e to the j omega naught n. Then I can write a as a magnitude of a e to the j phase of a. And then I can get something that looks like this for my x of n. And then if I had y of n, I'm going to have my complex exponential, this is this input, times the a, which is the same, just a constant gain, and then times a magnitude and a phase shift from the h. So this LTI system just causes a magnitude and phase shift to the input signal, this case e to the j omega n. So this means that LTI systems cannot create any new frequencies. So if you have, so let's like try to look at this in the context of like a real valued signal, because you know, we like to look at real valued signals a lot of the time. So let's take a cosine omega naught n, and let's take a simple system, this h of n, which is just 1 and then minus 1. This is 0. This is time 1, this is 1, this is minus 1. So this is my signal h of n, right? And I want to know what happens when I pass the cosine through this system. So it's very easy to kind of look at it just in terms of what the delta functions do. So delta of n makes a copy of x of n, and minus delta of n minus 1 makes a copy of minus x of n starting at time 1. So we can get cosine of omega naught n minus cosine of omega naught now n minus 1 starting at time 1, or shifted by 1 to the right, rather. Notice both terms have the same frequency, omega naught, so that means that we're not creating any new frequencies. The fundamental frequency of this discrete time signal remains the same. And more generally, if you have write h of n in terms of a series of delta functions here, then you can just kind of plug in the delta, with delta n minus k convolved with this cosine is just going to produce a cosine omega naught n minus k, because it's just delaying it by k, and then we're going to get this constant multiple hk, which comes from here. So now we can like say, sure, it's an infinite sum of cosines, but really what we would want, and what's actually true, is that this is a single cosine. And one thing to do would be to like do really complicated angle addition formulas and do a lot of trig stuff, and then try and massage it into one form. Or you can just use this eigenfunction property that we just saw and compute the answer in just a few lines. So let's go back to our original h of n, the simple h of n, and our xn, which is cosine omega naught n. So first thing we're going to do is Eulerize. So we Eulerize the cosine to get this. And what we need to do is we need to calculate, to use the eigenfunction approach, we need to calculate this function h of e to the j omega. And you might ask, well, okay, why is it function of e to the j omega? Part of that is a notational convenience, to remind us that it's coming from this series of e to the minus j omega k's. So this also helps us distinguish between when we're talking about discrete time signals versus continuous time signals. So we just need to calculate this thing, which is, remember, h is only non-zero for two values. For at time 0, h of k equals 0, e to the minus j omega 0 is 1. And then at time 1, you get e to the minus j omega, and there's a minus sign from this minus sign here. Okay, so the important thing to note is that if I'm going to need h of e to the j omega, and I'm also going to need omega naught, rather, and I'm going to need h of e to the minus j omega naught, because this is a minus j omega naught over here. So if I look at this function here, h of e to the j omega, and I write e to the minus j omega, just plugging in a minus in there, then I get 1 plus e to the j omega. And the important thing to note is this is actually just the complex conjugate of h of e to the j omega. And so if I write that in magnitude phase form, it's got the same magnitude as h of e to the j omega, so same magnitude, but then the phase is flipped. The phase is flipped. Right, so this will help us simplify things in a bit. So now, using the eigenfunction property, we can say that the output y of n is just h of e to the j omega times the first term up here, and then h of e to the j omega star, because of this relation here, times 1/2 e to the minus j omega n from up there. Okay, so what do we end up with? Well, we end up with, if we write things out in magnitude phase form, we can write it as magnitude h of e to the j omega, and then a phase, and then a magnitude, and a phase. And because the phase is flipped, remember we had this flipped phase from h star, when you took the complex conjugate of h of e to the j omega naught, the signs work out in this exponent here, and this thing just reduces to another cosine. It's a half times e to the j something plus a half e to the minus j times the same something, and that something is omega naught n plus phase of h of e to the j omega naught. Okay, So now we've got a lot of notations, omega naught, blah, blah, blah. It's just getting a little complicated. Let's just plug in the value of omega naught and see what we get. So let's take omega naught equals pi over 4. Right, then what we can see is that e to the minus j pi over 4, because we need to calculate h of e to the j omega naught. Well, that's just 1/2 minus 1/2 j. And so when we plug in, we calculate the actual value of this coefficient. It's going to be 1 minus 1 over square root of 2 plus 1 over square root of 2j. And then we can calculate the magnitude and phase from these two, from the Cartesian representation here. So we get the magnitude and the phase, and then we just plug it in. Magnitude, cosine pi over 4n, plus the phase. And we're done. Basically, just have to calculate some complex numbers, and then we're done. And so that sum of two cosines, which we had before, now is just, we can write it as just one cosine. Okay, so in general, because the phase is an odd function, in general, cosines are going to get, and this is if you sort of prove things in general, cosines are going to get a magnitude and phase shift. So if I had a cosine omega naught n plus phi, and a coefficient h of e to the j omega, that's basically this h of e to the j omega magnitude plus e to the j phase, then we're just going to get the magnitude plus the phase added to the cosine. And what we do is we call this the sinusoidal response to the system, because we're putting in a sinusoid, we're getting the sinusoid back out with the same frequency, but phase shifted and magnitude shifted. What this means is, of course, if you write an input signal as a linear combination of complex exponentials, then the output is going to have the same set of frequencies. That's really important. If I say I have cosines at omega 1, omega 2, and omega 3, at my output I'm going to get the same cosines with omega 1, omega 2, and omega 3, but the volumes might be different, that is, the magnitudes might be different, and they might be phase shifted a little bit. So the main sort of takeaways from this, there's sort of 3 points, which are kind of all consequences of this statement that I made before. Complex exponentials are eigenfunctions of LTI systems. Okay, so what does this mean, right? To be an eigenfunction means that if the input is a complex exponential, the output's also a complex exponential, but at the same frequency. So the point is that it's at the same frequency. And this means that LTI systems cannot create a new frequency that's not present in the inputs. And finally, that what you get from a sinusoid and complex exponentials when you put them in is that you get a magnitude and phase shift when you pass them through an LTI system. So these 3 facts are really important, and kind of they all work together to kind of show how complex exponentials are very special, have a special relationship with LTI systems, and that's this eigenfunction relationship. So of course, nothing to do left but to try calculating some sinusoidal responses. So here are a couple of examples for you to try on your own. And I encourage you to make some up as well. You'll have to get a little bit of practice, doing your complex numbers. But I think what you'll get is much simpler formulas. And in fact, you can discover new trig formulas if you like by doing this operation. Although that's kind of the byproduct of doing things this way. What we really care about is in the system, what if I put a sinusoid into my box? What am I going to get at the output? And how is it going to be different? And can I compensate for the phase? And all sorts of questions that come up when you're actually engineering and designing these systems. So it's important to be able to take a system and understand its impact on sinusoids in terms of magnitude and phase. So that's it for discrete time, and I guess the next thing we turn to is going to be continuous time convolution, and we'll see a lot of the same properties. A lot of it will just rhyme as we go through.